So we discussed node level problems. We discussed edge level problems. Now we are basically talking about clustering. So clustering is essentially soft graph level problem. So you are trying to partition nodes into a subset of nodes. So you want to, for example, say that detect some community, for example, within a collaboration graph that we discussed about. So what you have here is the graph itself. You don't have any information about the labels, type of basically whatever these are due. You just know that there is a connection between these people. So in the case of authorship problem, the collaboration graph, you only know that these people have been co-authors on the same paper, but you don't know what that paper was. You don't know anything about these people or anything like that. So let's assume that this is some graph, some collaboration graph, and these nodes are researchers or academics. And each edge is representing basically co-authorship between two different nodes. Now, when we deal with this type of problems, as I said, we are looking at the graph as whole. So we have the set of all nodes and the set of all edges. Those are our input information. Now, let's say that in the problem of community detection, we have this for a collaboration graph, and we would like to learn something from basically something underlying communities in this collaboration graph. Sometimes it might not actually represent anything, but if that graph actually has some latent type of communities within it, which we will have, for example, in a collaboration graph, it will basically help us to learn more about that basically collaboration graph. So that's the goal of clustering, for example, in this example. We cluster these and we figure out, okay, these are connected to each other. I mean, our algorithm, some algorithm says that, okay, this is one cluster, this is another cluster, and this is a third cluster. We look at that and we see that, okay, these people are actually from College of Science, these are from College of Engineering, and these are from College of Arts and Letters. So our basically model learns something inherent within that community. But that's not the only type of clustering that is possible. You have different clustering algorithms. It can learn, people collaborate based off of many things. For example, people of same age, same demography, same field, not necessarily from the same department, also collaborate with each other. So it can, based off of the method that you have, it can learn any type of clusters and basically any type of latent information from that graph. Two close concepts to clustering I'm going to review. One is connectedness. So what is a connected graph? A connected graph, a connected undirected graph, is a graph that there's a path between every pair of nodes in that graph. So let's say that here, I can go from V1 to this node, V3 and V4, but there is no connections between V1 and V5. So so this is not a connected graph. I look at the other one and I see that I can go to V1, I can go to V2, then I can come to V8, 9, and go to V5 from there. So there is and I can repeat that for every pair of nodes in that graph. So this is a connected graph. Now, each subset of connected nodes in a graph is called the components. So here, the maximal basically is the maximum number of nodes that are connected to each other. So here we have one component, because if we say that it's basically, if we only say that the nodes that are connected, you can select this as well. What's the maximum number of nodes that are connected? It's called a component. So here you can look at this as a component 1 and this one as component 2. Now, in this other one, every node is connected to each other. So the maximal set of nodes that are connected is the whole graph. So this whole graph is a single component. Now, an interesting property of connectedness essentially is that if you have two different components, you can order your adjacency matrix into block diagonal form. So here we can write our adjacency matrix as this form, where we have blocks of 1 and 0s on the diagonal, and everything else is 0 out of that. And each of these represent one of the components of this graph. So here, this top block is representing this bottom component, and this block is representing this component. You can look at each block as the adjacency matrix for the corresponding component. So if you take this component and write it as a separate graph, its adjacency matrix would be this way. So you combine different components, generate a whole graph. It's gonna have an adjacency matrix, block diagonal adjacency matrix, which is consists of blocks of adjacency matrices of its components. Now, I have another one, which is connected, and you can see that the difference between these two graphs is this edge. So this edge is the connection between two components, and we call that a bridge. So a bridge is usually seen here with a non-zero parameter, non-zero element outside of those diagonal blocks. So we had this component here, this bottom component up here, and this one is representing the connection between nodes, basically these two nodes. All right, so we looked at connectedness in undirected graphs. Now let's look at the same concept for directed graphs. It's a little bit more complex for directed graphs. We have two types of connections. For connectedness for directed graphs, we have strong connectedness and weak connectedness. So a strong connectedness in a directed graph means that there is a path from every node in that graph to every other node. So let's look at this one on top. We start from this node and we want to get here, right? So we can take this path to come here. And I can go the other way around. I can start from this guy, go this way and get to this node. And you can repeat that for every node in this graph. And you call that a strongly connected graph, directed graph. A big connectivity means that you can't get from, and you're basically looking at the direction of edges when you're traversing on the edges. So when you're going from one node to the other, there is always a basically path. If you can go from node 1 to 1, 2 in a connected graph, you can always come back on the same thing, right? Same edge, basically sets of edges, same path. But depending on the direction, in a directed graph, you can't do that. So there is no basically strong or weak for a connected graph. So let's say that, and it's a very simple example. All right, so let's call this V1, let's call this V2. You can connect to graph. If you can get from this to this, you can for sure get from V2 to V1 as well, right? Because there is no direction, there is no constraint on that. So now let's say that there are directions here. You can, following the directions, you can get from V1 to V2, right? So, but can you follow the directions and get from V2 to V1? You can. So that's basically called, so that this is not a strongly connected directed graph. Now, let's go to the concept of weak connectivity. which means that it is a directed graph, which is not strongly connected. But if you disregard the edges, it is a connected, undirected graph. So let's look at this. This node has only out edges. So this edge is pointing this way. This edge is pointing toward this node. So there is no way you can come from any of these three nodes and reach to any other of these three nodes, because the only path to get from this component, let's not call it component, from this subgraph to this subgraph is by pathing through these two edges. And this direction indicates that you can't go this way. So it means that it is not a strongly connected graph, because you can't go from any of these three to any of these three. But now let's disregard the directions, and let's say this is just an undirected graph. There is a connection, so there is an edge. Without looking at the direction, you would be able to come from any of these three nodes to any of these three nodes. So that's called a weakly connected, basically, directed graph. An example is World Wide Web. You are in a website, you click on a link, and you get to another web page, and there are no links there, and you can't go back by clicking on hyperlinks. You can click back, but that's not part of the graph. The graph is only the web pages and the hyperlinks from one web page to the other. So that means that the web is not a strongly connected graph. It's a weakly connected graph. Now, the same goes for citation graph. If you think about it, people only cite people before them, right? I mean, archive, you can cite people before the paper is out, but before that, you could only cite papers that were already out. So if you think about it, you go back directions. So always looking up, and there's no way to come back from basically the first paper cited ever to the current paper. So this is a weakly connected basically graph. But because of archive, it's almost weakly connected. Now, we had weak and strong connectivity. At the same time, we have weakly and strongly basically connected components. So, for example, look at this. We have three nodes here, and we can reach from any of these to any other one, right? So I can travel from this one to this one using these two paths. I can travel from this node to these two in this direction, right? Let's look at this one. The same thing applies for these three, but they can't reach to this. So each of these are weakly connected components, because there is no way to get from any of these to these, but regardless of their direction, these four are connected with each other. These three are connected with each other as well. Now, look at these. You can say that these three, always you can get from any of them to any other of them. So this is actually a strongly connected basically component. So the test for strong basically connectivity and weak connectivity says that it shouldn't be strong. So I should have tested the strong as well. So they passed the weak connectivity test, but it also passes the strong connectivity. So we say that this is a strongly connected component. These three are connected to each other as well. We call that another strongly connected component. And by definition, we basically, by convention, a single node is also a basically strongly connected component. So yeah, so that's basically the definition for weakly connected components and strongly connected components. So quick summary, we talked about different tasks on graphs. We talked about node level tasks, which included node classification, we studied different type of strategies, which included homophily, equivalence, and heterophily. Which basically homophily meant that two nodes that have similar attributes tend to interact with each other. Equivalence was looking at the neighborhood structure, and heterophily was saying that two nodes that have dissimilar attributes will interact with each other. We looked at edge-level tasks, which included link prediction. We looked at two different graphs, heterogeneous graphs and hypergraphs. And lastly, we looked at bipartite and multipartite graphs. So these were different type of graphs that you encountered when you were looking at the link prediction problems. So we looked at subgraph level tasks, including clustering, and we looked at different concepts related to clustering, including connectedness and components that we'll revisit later.